delighted to introduce the first of our speakers this afternoon, Thomas Schick, who will talk about twisted spin-C Fordism and twisted K-homology.
Should have added the names of my co-authors, I guess. Roman, Michael Lachim, Mehdi Kouami. So, yeah, how to start? There are two ways to start, right? Either you start with the story and you get to the result at the end, or you do it the other way around. So I talked about this subject at this place, the Newton Institute in Cambridge, a year ago, but it was a different audience, I think, zero overlap. Anyone? So it's okay. And I decided at least to change that order. So now I'm giving the result at the beginning and then the story to explain what it's about. So there is a theorem, which there are two theorems, which both make a relation between twisted spin-C manifolds and twisted K-homology. And the first one is a twisted version of a theorem of consequence and Hobbe. And let me just save it. And of course, there's stuff to be explained later, story part. So that's easy. We start with a space, let's say a compact CW complex. Generally, we are used to applying this kind of theories to spaces, right? Fordism or K-homology. And then there's a twist part. So we also have this. How that's actually a map from X to a model for the classifying space of P of H. So let me just add some background here. H is a separable Hilbert space to fixing, like there are two functions on Z, something like that. And P of H is the unity group of that Hilbert space, which is a contractible group by Kuiper's theorem, modeled out stuff in the center. And from that computation, this is contractible. That's a subgroup which is U1, so a circle. We see that this thing has a homotopy type of a KZ2, and this thing has a homotopy of a KZ3. So, and that is a new twist. So we have a space and a twist, and then we can compute, perhaps, or define, talk about twisted homology. And the idea is to compute the twisted K-homology. Let me write it like so. I'm thinking of degree as also some kind of a twist, and we can combine it with this other twist. So this is just some notation defining twisted K-homology where I use this twist tau. I'm going to talk about this a bit more later. Of the space X, this is what we compute, and this Hopkins-Hobbe theorem says, the title of the Hopkins-Hobbe theorem is spin-C Fordism determines K-homology, and it's just the same here, only that everything is twisted. So and how does it determine? Well, you would expect that there is some way to take spin-C Fordism of X, and now it's twisted, so I have to tau, and get out of that this here. And the way this is working, following is very simple and very surprising. This is, with or without a twist, a module over spin-C Fordism of a point, which is a ring. So we can tensor this module over this ring with any other module, and what module might come up here to get K-homology? Well, the module K-homology of a point. So where this becomes modulo over that by the canonical orientation map from spin-C Fordism to K-homology, which is of course a ring homomorphism, in particular makes this a module over that. Okay, So that is result, this canonical map, which is isomorphism. Now let me comment on this. This is not because this module would be flat with this ring, which would then say if we have a homology theory with tensor with a flat module, we get a new homology theory, and then what else could it be or this? I mean, that would actually be very easy. If you knew there's a flat module, it would be easy to make this homomorphism. It would be easy to check that it's the identity on the point, and so it would be an isomorphism for all spaces. But this is not the case. This is not flat for this, so we'll have to work harder. And this is somehow in the ballpark of the Landweber-Funke theorem, which is exactly about this situation. We're not yet a step beyond. The Landweber theory doesn't apply here, so Hopkins and Howe had to work for this particular situation to get this done, and they used for that the Anderson-Brown-Peterson splitting of spin-C Fordism in a significant way, and we're using a twisted version of that, based on twisted Anderson-Brown-Peterson splitting, and this twisted version is due to Hagen-Hedenstreit and Michael Rath. Everything about that. Okay, and more things. So it's not just taking this. I have to work more. Okay, so that's result number one. And we use this. This gives also as a key ingredient a second theorem. Again, is by Prof, which let me shorthand as Wang's twisted MEP model for twisted K-homology. Statement number two. There's a certain group defined by Wang, which he claimed to be isomorphic in canonical way to this twisted K-homology of X. And with the proof, I couldn't work out, couldn't understand, neither did Paul Baum. And I was quite upset with that because Wang was insisting somehow works, but his arguments are just not the kind of arguments I can follow, at least. So I was working for quite a while to disprove this theorem. It had the touch of not being correct. The way these MEP things are manipulated in other situations just don't work with what he's doing. So it seemed like something is fishy there. So now I'm a bit unhappy with this result because it somehow shows that for 2 years I was just working toward the wrong direction. It does work. So this precisely, let me tell you what that is. It's Wang's MEP model. The group of turbulence classes of cycles. That is how an honest, nice geometric homology should be made, right? You're writing down certain cycles, which are hopefully quite nice. I like Fordism a lot because the cycles are really nice. And then you impose a certain equivalence relation, you understand less, and you get a group out, and that is what for someone who is geometrically inclined is a nice homology theory. For most of you, it would rather be a spectrum and stuff like that, but it is not so bad to have as well. I mean, there is of course a spectrum definition of twisted K-homology, which coincides with what we're doing here. But this is geometrically inclined one. Cycles. So what is it? The cycles are these things, M's. This is a closed manifold. I's. This is a map to X. E is just the usual world, when you see such cycles, there would be more structure on the end. Typically, it would, for K-homology, it would be a spin C structure. Now we are in a situation that we want to talk about a twisted K-homology, so we replace the spin C structure by a twisted spin C structure. So now these twisted spin C structures have to use the twist tau. And how is it done here? Now, of course, we have the map tau to BQ or KZ3. Let me write back KZ3. And I'm explaining in a second that given such a map to KZ3, we can talk about a twisted for that map spin C structure. And this we have to choose with a tau composed with phi twisted spin C structure on it. Now, some tiny bit of motivation why one wanted this model in particular. Such a twisted spin C structure doesn't always exist. Neither does an honest spin C structure always exist. So we do expect some condition here. Physicists use such objects in certain types of string theory. This would be a background space-time, and this M would be something they map in this models. And the existence of such a twisted spin C structure would be a anomaly cancellation condition. These are words I read in their papers. I mean, this is what the meaning is, a mathematical one, and has some physical significance as well, of course. Fried-Hopkins anomaly cancellation condition, making certain terms in certain position functions well defined. We have an exponential, and then we want that something cancels out. Exponent of 2 pi I of some number, which better is an integer, so that eventually doesn't matter. Okay, so these are the cycles. And I also tell you what the rotation is. And I'm going to talk about this twisted spin C structure in a second. A story, right? With equivalence relation generated by, so there are 3 things. One of them is Bordism, and you can work out what Bordism means. All the structure which we see here has to be carried along with Bordism. Okay? Including the bundle, of course, including this twisted C structure. The second one is a somewhat technical one. It means direct sum of vector bundles. If you have 2 things which are equal, but the bundle, you can do the sum of the bundles. And another thing you can do, and that should be equivalent, is the same as disjoint union. Which of course is also something you can do. I never said M should be connected. I also didn't say M should have a fixed dimension. Very flexible there, and just has to be compact. This disjoint union is the group structure. After all, this should become an abelian group at some point, and that's the addition that we should expect. So it's very much a Bordism model with some decoration. Okay, what is the third thing? The third thing is a bit more complicated. It's called vector bundle modification using spin C vector bundles. You could restrict to just using complex vector bundles, which are real even dimensional and have a canonical spin. Okay, so what is this doing? If you have
when you say equivalence relation generated by direct sum, you mean sums of these things are equal to the disjoint union?
So I said here, if you have 2 of these cycles, ME1 and ME2, everything the same, that you want to do are whatever they are. You can form the direct sum, so you get an ME1 plus E2 phi,
Yes.
and that is equivalent to, you take the disjoint union of M with itself, the disjoint union will map with itself, that's just repeating, and you have the two bundles on the two different components. This disjoint union you can do for arbitrary cycles. Of course, this you can only do if the underlying M is and P is twice the same. And in that case, the two should be equivalent. And in general, this disjoint union operation defines the group structure of this. Of course, you have to think, as usual, about the inverses, and as usual, it works by inverting this twisted structure. So, do I want to go much into details here? No, I don't. This changes M to, let's say, the traditional way it's done, the sphere bundle of this new vector bundle, let me call it F. Okay, so that's an even, because F was even dimension of sphere bundle here also consisting of even dimensional spheres. We change the dimension from one dimension to a bigger one. So cycles of different dimension are equivalent here. And you have to do something to the E and the phi. The phi is just a projection, and the E you have to use multiplicity to get it right. You expect something like that to appear, because if you ever have heard something about K-theory, you know it satisfies multiplicity. So there shouldn't be Z many different groups, there should be two different groups, an even and odd group. But if we have a manifold around it has an integer dimension, this now is responsible for making a theory such that multiplicity. Let me make a comment on this. What I said before, when you manipulate with these MEPs, what you typically want to do is to replace the cycles by some special cycles. And one way to do that is to take M and get rid of the manifold part by embedding M into a high-dimensional sphere, you can always do, and then use the vector bundle modification with a normal bundle to get something of a special type. Now, this works nicely, but it doesn't work nicely here because if you do this embedding of your non-spin manifold, non-spin C manifold into a high-dimensional sphere, its normal bundle will not be a spin C vector bundle. It's just not true. It's precisely true if the manifold has a spin C structure that the normal bundle has a spin C structure. So here is somehow things different from how they should be, and that is what was shown. So you couldn't do the usual manipulations to work with these kind of cycles, make them easier because of this obstacle. Okay, here are the theorems, and we're still owing you something. I'm owing you all about this twisted, what isn't twisted K-homology, twisted spin C structures. Now let's maybe step back quite a bit. If we talk about homology theory, we fix our category of topological spaces, and then we say it's a functor on that category or certain data including functor and after transformation, satisfying certain structures, certain properties. Now we have the twist around, so this twist also has to come in, and for that I'm making the following ansatz. We work with twists and find us. So functor twist from our category of spaces, two group points. So each time I have a space, I get a whole group point, the object of group point as twists. And there's more than just having the twists themselves. The twists have morphisms between them, automorphisms, but only if all morphisms are isomorphisms. You could improve that by having something like higher morphisms around, but I'm sticking to this somewhat simpler model. There's just twists, and there are morphisms which are isomorphisms between twists. Okay. But this is factorial, and some people then say it's a cosheaf. pre-sheaf, and I wanted not co-sheaf, I wanted contrariant functor here. Pull back twist. Pre-sheaf with values in group weights. There's one extra, so that's what a twist should be, just this kind of information with one extra structure, a trivial twist. Each twist of X, each of these group weights has a trivial twist, special. With all the pattern requirements. Of course, if you later on we form this twisted homology, if you insert a triple twist, use that as homology. Untwisted ordinary spin C was untwisted ordinary K-homology. Right, that's all I need. Let's look at samples which are coming up here, which we need. One of them would be I define twist effects to be all P of H principal bundles over X. Of course, with principal bundle maps as the morphism, they're automatically isomorphisms. So that is one way to define twists. And let me do another one. So there are often different choices, which is coming up there, and the two are very closely related. I could take maps, fixed maps from X to a fixed model of PPU of H, which we saw previously in KZ3. So we fix the space, and then we look at each element in twist of X is one such map. Now, what are the morphisms here? They're homotopies by definition. Okay. And you see a nice functor from this to that. Just pull back the canonical principal bundle. The universal PU bundle which lives over dPu of H. And we didn't talk about it, but of course we need this functorality just given by pullback or by composition. And you see the two things are working quite nicely together. But observe also that it's not exactly the same. There's certain.
So do you literally mean homotopies or homotopy classes?
Very good.
Because if you take
This
homotopy
was
classes, you don't get. No, but then you don't get.
I wanted to stick to this model, and there you see that you could do refinement higher.
Now, if you have a homotopy class of homotopies, you don't get an actual map of you just get some sort of connection from some.
They are certainly connected.
Through a theoretical.
Right. So there is. It's convenient this way, but there are certain reasons to go to this higher structures. Right. So, you could come up with all kinds of other things which could be twists. There's not too much required there. Let us observe here that and I guess we're able to allow homotopy classes of bundle maps, and they will be fine. So, go to right. Okay. I wanted to say that in both cases. isoclasses in twist of X. These two cases are given by the third homology with integer coefficients. It's only very visible here in our discussion. This is a classifying space for this. So this is what you might have seen in some papers, that a twist is a class in H3 of X. But that's a bit dangerous because it's important to keep into account that there are automorphisms of those. And if you just fix an isomorphism of something, how can you talk about isomorphism between isomorphism classes? Good. So, twisted generalized homology. Now a functor. I don't really know how to write all that. So it assigns to a space with a twist, this graded group, and it's functorial in the twists, and it's functorial in the map between spaces. Is there a good word for that? Maybe, yeah. But this would be the abstract setting. If you have an abstract twist of X assignment, then you can form that as a functor. Factorial covariantly in these morphisms between twists, and maybe also covariantly factorial into homology in maps X. To be more precise, what does this mean? We will be able to map 2 E star plus tau X or tau twist on X from, well, the only place where it makes sense to start. You can pull back this twist with F. And then we have the corresponding group, and we want satisfying axioms you can work out, as you know, network homology theory, particularly as a Myvitoris principle and decision and stuff like that. I didn't write out pairs. Maybe we should extend that to pairs. Yeah. So this is a sketch of what this is, and dual homology was also a version of homological, which I'm writing down because I can give you a very quick definition of twisted K theory. So if tau is one of our maps from X to B PU, I define the tau twisted K theory of X using K theory's C-star algebras. So we need to assign a C-star algebra to the space X, to the functions out of X, to the complex numbers. But this is not good enough because we also have to take this tau into account. And how is that done? You take the bundle tau star EPU, that's a PU principal bundle. Now PU acts by automorphisms on a nice C-star algebra. In the C-star algebra of compact operators on the Hilbert space H, just by conjugation. A unitary acts by conjugation and preserves compactness, and the center acts trivially by conjugation. So factors through PU. So we can make, this is now a bundle whose fibers are isomorphic in a non-canonical way to the compact operators on our standard Hilbert space. So from a certain K-theory point of view, that didn't make much of a difference. Compact operators and complex numbers are pretty much the same. But we have changed a little bit because we have this twist. That's just enough to make the change we want. Now we can make the sections of this bundle of fibers are compact operators, or C-star algebras. That is going to be a C-star algebra by pointwise multiplication. You have one section, you multiply with a second, you get a new one. And this is a nice C-star algebra, it has a K-theory, and that is a quick definition. So you see one example. Fine. For you, of course, you have to check that this satisfies maximum. But the functionality properties are easy to get. Just putting back the bundle induces a map between section algebras, and that gives you what you need. The functionality is not so much.
Is PU the full group of automorphisms of their compact operators?
It is.
Okay.
We use standard norm topology. So this is not exactly a model using vector bundles. It is somehow has an infinite dimensional touch to it. It's like infinite dimensional vector bundles in some sense. And it can be shown that you can't get away, what can be shown, with certain standard attempts, you will not be able to define twisted K-theory using something a bit more general, but like finite dimensional vectors. You have to put in some infinite dimensional stuff. The exception is if this twist, which is classified by third integer homology class, if that is a torsion twist, then you can get away with vector bundle-ish finite dimensional objects. What is even more problematic is to talk about K-homology in a geometric way. We know that already for the classical K-theory, the vector bundle picture was there. It's very beautiful. K-homology is there kind of automatically from the homotopy theory point of view, but making a nice geometric model took a while. And the MEV model we saw came about at some point, but I think it's quite a few years after the definition of K-theory. Baum always says that he was looking for such a model for a long while. So I can't write down an easy model for K-homology with a twist, except for we have theorems, right? So those. Maybe just in words, the second motivation why you might want to talk about twisted versions of homology theories and homology theories. If you're interested in orientations and push-down maps which use orientations, and you don't have an orientation, there is always a certain twisted group which is canonically there, which has a canonical twisted fundamental class, and the push-down is possible. So this is one way to get out of this problem. You want to pretend things are as if they were oriented. Twisted word will help you there.
Thomas, then you need to make everything Z2-related. So does the
For the K?
Yeah, I mean this only captures. I mean the map from. So what do you say? The J homomorphism from BO into BGL1KO does not factor through DPU. Only the connective cover. Like you need an oriented manifold to get a twist like this. Otherwise, you get a twist in
Okay. Yeah.
PU of a Z2-related space. So is that just saying the right words and everything works out, or is there?
I think I wanted to just claim that there is good reasons to look at that without going too much into details here.
Yeah.
So if you want spin structures or spin C structures for oriented manifold, that works very nicely, even if they don't exist on the nose. Let us actually maybe go to that right now, because we still raised. Well, maybe another thing I wanted to show as an example here. If you believe in this, there is the trivial twist, which just gives us an ordinary theory. and or K-theory, the whole thing. And we also learned that twists have automorphisms, and these act then on this ordinary homology as well. Let's look at that. Twists have automorphisms. Here, for the trivial twist, so what was it? We just took the constant map to K3 and an homotopy class of the homotopy from the constant map to the constant map. What is this? Here, so that's a trivial twist. You get a map from X to loops on KC3. Homotopy class of map to loops from KC3, so we get a map. Which is of course KC2. So certainly should see in our two models, in our two examples, an action of H2 on ordinary whatever, K-theory, let's say. Given by this automorphism acting on, let's say, K-theory of X by. Okay, but this is also two, a CP infinity or BPU1, so that classifies line bundles. Each time we have such an object, we have a corresponding line bundle. So and here we just tensor with the classified line bundle. Work out that this is what's happening, but what else could it be, right? So that's in some sense the basis of how this goes. If you see something like this happening, that there's a canonical action here in this case of H2 of X, initial coefficients on a certain homology theory of the X, natural in the way it's obviously here, it smells like there should be some word with twists and twisted theory in the background, where this then is just the manifestation of how the automorphism of the trivial twist act. Let's also analyze what happens on spin C, ordism of X. Well, again, we have this line bundle, and now one should, that's a fact, if you have a spin C structure, I mean, after all, these are manifolds with spin C structure, on the spin C structure, mapping to X, you can change the spin C structure by tensoring with a complex line bundle. That's one fact about spin C structures. By changing spin C structure via the line bundle. So that fits kind of nicely. But this is all. So this explains a tiny, some aspect of this twisted theory in the untwisted work. Okay. See it there. Now let me define twisted spin C bodism, which was in the twisted Soviet theorem what we saw kind of in the first theorem. Twisted spin C bodism, all I need to explain is what a twisted spin C structure is. And recall what we manufactured. I had the manifold M, which was a closed manifold, and using this composition of two maps, we had a map to KZ3. We had a fixed model once and for all for that. So this is the information given, and that, I mean, with this information, we have to define what a twisted spin C structure for this kind of information is. Let me write F here, because F of phi composed with F before. Now, what is this KZ3? That's the target of the third integral Stiefel-Whitney class from BSO, ABC orientations again. And this third Stiefel-Whitney class is precisely the obstruction for a oriented vector bundle to admit a spin C structure. The fiber of this map is spin C. Now I'm drawing a non-commuting diagram. Okay? But there is, of course, a diagram. M has a stable normal bundle, which is classified by a map VSO. Just write the normal bundle here. And I have, again, you have to be a bit precise here. One has to fix these spaces and to fix the map concretely. Honestly, it's not enough to say everything's a homotopy. In the end, there is a homotopy relation, but the objects have to be precise. So what is kind of information given? What would be a spin C structure on M? Well, it would be, we have this map, and we choose a lift of it to be spin C. That doesn't see this, but you can reinterpret this as saying it's a homotopy of this composition to the constant map. It's pretty much the same as choosing a lift. Okay, now we know how we do the twisted version. We can talk about the lift, but we can still speak about the homotopy. But now the homotopy should be between this composition and the given map. For F is a homotopy H between a classifying map for the tangent bundle and this model for the third Whitney class map, and for the F was the statement which was given. So now we know what a twisted spin C structure is, and then you have to take classes of such things. So the maps are precise, but then you take homotopies of such terms. So, due to this twisted object solving theorem, if you believe it, you can now work out could be a definition of twisted K-homology, particular tensor program. What would the homotopy theorists do to define twisted homology, twisted homology? Well, as we discussed before, there's different words in which you could work, and maybe I'm sticking to something a bit old-fashioned. You could work with some infinity structures, higher structures, or you could try to be as concrete as possible, which I'm following the Joachim paper they do it there, very concretely. So if it happens, if you manage, so in our model, yeah, our situation, to produce concrete, let's say, orthogonal spectrum, so really for orthogonal vector spaces, and the corresponding structure maps between them are all honest and precise, with compatible action of, well, always in the background we had our group PU of H. But if you manage to do that, you can do an associated bundle construction. Right? I mean, you have to be quite precise if you want to do associated bundle constructions, but if everything is strict, you can certainly do that. You can do recall that we had these two versions of our twists. One of them was just PU principal bundles. By each time we have a PU principal bundle, we can, and we have all this very strict spaces around, we can just do the associated bundle construction throughout, and get then a bundle of spectra over X. Sequence of spaces with maps relating, characteristic, what they call maps between the different spaces, suspensions of those, and so on and so on. So that can all be done if you manage to do all of that. And great. You have to do this. So this is this spaces with all these PU actions for K-theory in C-Bordism and C-local connective L1 local versions. There's a long list of things all done. So we have all kinds of twisted, all kinds of situations where you can make these bundles of spectra. K-theory, for connective K-theory, spin C, Bordism, or some localized version of that, and so on and so on. Define this bundle tau. Define tau twisted homology by, so if you have a bundle of spectra, we have these spaces, and each fiber has a base point. Right, so that's a little odd because typically we have just one base point, but we have a bundle and each fiber has a base point. Now topologists know what to do. They collapse all these many base points to one. Then you left out with one. Collapse the fiberwise base points. So then we get a sequence of spaces, each with a single base point, and then we can take the usual stable homotopy groups. So for example, for them the twisted K-homology of X would be to take these homotopy groups. What are we doing? We do P, we associate to it this particular mod of the K-theory spectrum. We mod out the base points to 1, and then we get these spaces and we take the homotopy group of those. Just right? So that is a homotopy theorist version of defining this.
So the geometrist version.
Geometers, I don't know. You could, of course, wonder how you can do this even more generally. And you can do this much more generally for a ring spectrum in general. You could indeed twist with all of GL1 of the spectrum. And for the K-theory spectrum, for example, the twist I'm describing here, this PU of H, is just a tiny part of what exists in terms of twists. But those seem to be those which are popular with geometers and physicists who are concentrating on those. And the claim is that this definition, and even the more fancy one, which works in even greater generality, is canonically isomorphic to what I described before in geometric terms. Okay. So for the spin C version, this is a theorem for the K-homology of this. Okay, so now we are we know what we're talking about and what these theorems are really about. About computing these groups defined here geometrically. Okay. So maybe at the very last. So our theorems. Good. And once again, we have the spin C X, the twisted tau, the map dp of h, tensor product over point, K-homology of a point, we want to map the twisted K-homology of X, that's an isomorphism, and we have this, the other thing that we have the K1 of X, so this group made of cycles. It is not too hard to see two things. One is that after all, these cycles are spin C manifolds with a twist and a certain extra structure. This is also spin C manifold with a twist, and then we do some factorization of it. In reality, there's a certain quotient is here. It's not hard to see that there is a canonical map here. Take the spin C manifold with a twist and assign it the spin C manifold with a twist. We have to add to it a bundle. The bundle is the trivial bundle, or maybe if, I mean, what is this? This is a couple of Z's, and then a certain fuzzy degree, which says it's 2 periodic. So this number here, you should take as, I mean, the trivial bundle with that dimension. It's a canonical map. And this map here factors over that one. So, this is very easy to see that this is well defined, it's not hard. Which tells you something immediately and for free. The Wang model is at least filling up the K-homology. Right? Because if you have an isomorphism and something factoring through it, it won't. I mean, this is the right thing plus some odd stuff we don't like. It should be 0. Right, so to prove that this is good, we have done half the work already. Great theory. This is something stronger than that this is isomorphism. And it's harder to prove. I mean, in the classical case without the tau. So, are related by diagram, and well, one way to prove injectivity is to prove surjectivity of this map. Right. Then completely done. And this follows from a normalization of these T cycles. I mean, a priori these are strange, and in particular, they're not necessarily the image of the map from above, because they have the complicated bundle part in it. So we want to normalize them to get rid of the complicated bundle. 2 cycles trivial E. If you get a cycle with a trivial E, by definition, that's in the image of the maximum above. And via the splitting principle, so there is a trick to make these cycles equivalent to other cycles or sums of such, that's where we only see line bundles. This is maybe splitting principle part. And then line bundle goes into the spin C structure. Discussed before that that's something which can be done. If you have a line bundle, we can change the spin C structure with it. We have to show that within this equivalence relation, which we defined, that's precisely a move which is allowed. Making the line bundle trivial and changing the spin C structure on the manifold instead. That is an equivalent cycle. So you should prove that, and you get the surjectivity, and you get the statement about 1. So that's how we finally got 1. I'm, I guess, more or less out of time, so I'm just stopping here.
Some questions?
Sort of, I guess, slightly mean one. I mean, Ulrich Penning showed that you can get all higher twists of K-theory as well using C-star algebras, right? The automorphisms of the compact operators are only PU, but the automorphisms of the compact operators tensor the infinite Kunz algebra are the entirety of GL1K. So that somehow gives an operator theorem model on the right-hand side. But I mean, there's no reason to expect this can be described any sort of spin C things. Because spin C is somehow tied to the lower Stiefel-Whitney class. Any idea what to replace the left-hand side by together?
I mean, as I kind of indicated, I think the first thing one should understand is how the new automorphisms really do something geometrically. They act on A-theory, and if you want to get some relation to spin C ball, you have to lift this somehow to spin C ball.
I wouldn't expect spin C boardism to play a role anymore.
Right. So I don't know.
Manifolds with an O infinity algebra bundle over them.
Yeah, I mean, if you do that, then you, I don't know whether this is very geometric. But then, yeah, you can put all the action probably in something very infinite dimensional and complicated coming from C-star algebra. That is likely, yeah. He doesn't do it, right?
Early on, you said something about if the twisting was torsion,
Yes.
then everything could be done a finite dimensional way.
So this refers to the K-theory. We saw that somewhere in the background, or this twist was described by in this operator theoretic way, by a bundle where the fibers are the compact operators. That's of course infinite dimensional. Now, and for the C-star people, the complex numbers and the compact operators are very related, Rita equivalent. And then there's things in between. There are finite dimensional matrix algebras in between, Mn of C. So it turns out that if you have a torsion twist, the corresponding bundle of compact operators can be replaced by a Rita equivalent one where the fibers are finite dimensional matrix algebras, still twisted, some kind of Azumaya algebra bundle, probably Azumaya bundle that would be what the algebraic geometers would know how they would denote this. And then if you have this structure, you can ask for, so this is somehow a bundle of algebras. Vector bundles are bundles where the fibers are modules over the complex numbers. Finally generate projective modules over the complex numbers. Now we have a bundle of algebras. We could talk about objects, which are fiber-wise modules over this bundle of algebras, and finally generate projective. These are, of course, also vector bundles, but they're a bit more because they have this action of this matrix algebra on them, and this matrix algebra changes from point to point in a way it's isomorphic to the Mn of C, but it's not canonically so. So these are exactly the finite dimensional objects I'm talking about. They're very close to vector bundles, and you can make a Grothendieck group using them, and that gives you precisely the even twisted K-theory in this torsion twist case. The problem is that you need a matrix algebra bundle to start with to talk about these finite dimensional objects. And so it's a theorem that this works and is precisely what we want. The K-homology picture, I really don't see a difference. I mean, it's not visible that the torsion twist is somehow special. For the K-theory, there's this phenomenon.
Is there a version of the exact functor theorem for M spin or M spin C?
This is,
Would you alluded to
if I
it,
understand it, it's just a bit off the Landweber exact functor theorem. So, is it at least Hopkins and Hove? Can one say that? I mean, there's when you prove what B and Hopkins and Hove, you have to do this differently away from 2 and at the prime 2. At the prime 2, you use the Anderson-Tom-Peterson splitting. Away from 2, you use a different trick. And for us, it was actually, for Hopkins and Hove, the away from 2 part was not so difficult. It's like something which is along the very classical results. But for us, this was actually the more difficult. It doesn't work the way Hopkins and Hove are doing it, so we had to do something new. Using in the end a theorem of Orami, which he calls the universal coefficient theorem. So that's another interesting result. And it's an ingredient for us. So if you want to compute twisted K-homology or K-theory of X, and tau was such a P-group bundle, well, what do UCTs do to us? They relate one kind of homology. Here the twist is a difficult thing. We want to get rid of the twist. And he does it as follows. He says, let's look at the untwisted K-homology of the total space P. Why not? I mean, this is not going to be the same. Now this is a PU of H bundle. PU of H is a group, so K-homology of PU of H is a ring with a Pontryagin product. And this is a module for that ring because of the PU of H principal bundle structure. Yeah. PU of H multiplies with P to P, so this induces a module structure for this Pontryagin product. And again, we can do this, we can tensor, this uses this Pontryagin product, Pontryagin module structure, over what? Well, K of a point again. We have to be a bit careful how you make this module over this. But this is what he proves. It's a pretty result.
That it's an isomorphism.
And that this is an isomorphism. Also that there's a map, the math is not so hard. This is an isomorphism, and it's very special. Initially we thought, well, if this holds for K theory, it should also hold for spin C-Bordism. After all, they're very close. But that's not true. The spin C-Bordism, the corresponding result is just wrong. Easiest case is X, the 3 sphere. So the smallest space where you can have a non-trivial twist at all, in our world, which has a H3 with Z coefficients, is already a counterexample with such a result for other homology theories. But this is a very nice way out, and for example, if you want to talk about K-homology with a twist, this allows you to reduce many questions to K-homology without a twist. For example, the Hopkins-Hove theorem works on this side. We were using this way.
Thank you. I think in order to have enough time for cookies,